Atoms consist of electrons, protons, and neutrons. The latter two are further composed of quarks. But you can make other stuff by arranging quarks in other different ways, such as the neutral pi meson made of a quark and its antimatter version. Now let's talk about spin. Angular momentum is a quantity that objects have depending on how much they are rotating. And just like regular momentum, angular momentum is also conserved. The total amount of it doesn't change over time. Now spin is something that only quantum particles have. It's some angular momentum they possess even though they aren't actually rotating. Remember the neutral pi meson from earlier? It has a spin of 0. Now this meson decays extremely quickly into 2 photons or particles of light, and because angular momentum must be conserved, the total spin of the 2 photons must also be 0. It turns out that photons always have a spin of plus or minus 1, so we know that one of them has a spin of plus 1 and the other minus 1. But here's what's weird. Until they're measured, the photons are both spin plus 1 and minus 1 at the same time, and only when you measure one, it randomly collapses into a state of either spin plus 1 or spin minus 1. But you know the total spin has to be 0, so you instantly know the spin of the other photon too, no matter how far away it is. And if your friend measures it, they too will see the same spin that you measured. So does this allow information to travel faster than light, breaking relativity? Don't worry, it doesn't. The reason is in the description.